Systems are covered in Section 5 of the tape. Conventional turntables use a stylus which actually contacts the disc, following grooves cut into the surface of a recording to pick up and, through the cartridge, transfer the signals to be processed. The CD player uses a sharply focused beam of light from an integrated laser pickup assembly for the same purpose. Just as the condition of the stylus determines the quality of the signal extracted from a recording, the degree of focus and the intensity of the light beam affect the quality and amplitude of disc signals. If the beam is severely out of focus, the extracted signals are marginal and can result in skipping or no audio, symptoms very similar to those of a worn stylus. Alignment of the stylus with the grooves cut into a recording is largely a mechanical function, requiring only that the tone arm be weighted in some manner so that the stylus tracts or stays within the groove and does not skip from one groove to another. An adjustable tone arm weight is generally used for this purpose. Compact discs do not have grooves, nor does the pickup device directly contact the surface of the disc. Additional beams of light from the laser pickup are used to determine and correct the position of the pickup by feeding information to a tracking circuit within the player. Tracking error signals are generated by the pickup assembly, amplified by the tracking circuitry, and directed back to the pickup to control the internal tracking device. If tracking correction is too great, the CD player generally registers error. Insufficient tracking correction will result in track skipping. A detailed description of the tracking circuitry is found in Section 4 of the tape. To summarize, then, CD players must coordinate 4 functions in order to play a disc. 1. Activate the laser. 2. Focus the laser beam. 3. Apply tracking control to the pickup assembly. And 4. Activate the disk drive system to rotate and control the speed of the disk. Let's take a look now at the sequence of operations as applied to a typical CD player. Most players follow one of 2 basic operational sequences. The first operational format automatically reads a table of contents at the start of the disk as soon as the disk is inserted into the player. When the table of contents is read, the player goes into the stop mode. The play button must then be pressed to engage normal play. The second operational format does not automatically read the table of contents when a disk is inserted. When the play button is pressed, the table of contents is read and the unit automatically engages the play mode. Both formats are operationally similar with these exceptions. For the purpose of explanation, we will concentrate on the first operational format. When a disc is inserted in the player, the laser diode in the pickup assembly is activated. At the same time, the focus circuitry is enabled. The unit searches for good focus, and when found, the tracking and disk drive circuits are activated. The disc rotates and the table of contents is read, after which the player goes into the stop mode. When the play button is pressed, the laser, focus, tracking, and disk drive circuits are activated, and the disc is played. Now let's correlate the sequence of operation with the overall block diagram of a typical compact disc player. When a disc is inserted, the laser diode is activated. If no light is emitted from the laser, the unit registers error and goes into the stop mode. If the amount of light is insufficient, or laser power is low, the unit might play, but will intermittently register error and stop, or intermittently skip tracks while playing. Laser power measurement and adjustments are covered in Section 2 of the tape. The focus circuitry is activated at the same time as the laser diode. When the focus circuitry is activated, it searches for good focus, and when found, amplifies the focus error voltage from the pickup assembly and applies it back to the lens control circuitry in the pickup. If good focus is not found, the unit registers error and goes into the stop mode before the disc rotates. If focus is found, the tracking and disk drive circuits are enabled, allowing the disk to rotate, and the table of contents is read. The player will engage the stop mode following this operation. If focus is not maintained, the disk will rotate momentarily, but the table of contents will not be read and the unit will register error. The focus circuitry is described in detail in Section 3 of the tape. Even if a tracking or disk drive problem exists, the table of contents will usually be read. However, the unit will usually register error and stop when the play mode is engaged. Pressing the play button activates the play mode by enabling the laser diode, focus, tracking, and disk drive circuitry. The signal processing circuitry in a disk player receives the digital data from the disk and amplifies, demodulates, and converts it to analog right and left channel signals. The PLL clock circuitry generates a 4.321 MHz signal that is synchronized to the digital data from the disk. The clock signal is required in the demodulation process and is also directed to the disk drive circuitry. An incorrect PLL clock frequency would denote incorrect disk rotational speed. The digital signal from the pickup is viewable after amplification. The wave shape is an I-pattern waveform and is referred to as the high-frequency HF signal or the radio frequency RF signal, depending on the specific model disk player. The I-pattern waveform is one of the more common signals used during alignment. It is used when performing many of the servo circuitry and pickup assembly adjustments. Problems in the signal processing circuitry are rare. If one does exist, the unit will usually remain in the play mode, and the problem will be apparent in the reproduced audio. If a problem exists in the PLL clock circuitry, it would appear as a disk drive problem, and error would be registered. On most compact disc players, the laser power emitted from the pickup lens is very low, approximately 0.3 to 0.4 milliwatts. In addition, the focal point of the beam is only 1 millimeter away from the lens. With the low power level and extremely close focal point, there is little chance of injury from the laser. However, as a safeguard, we suggest not looking back through the lens at the laser. The pickup assembly itself is not considered serviceable and is treated as an individual component. However, it must be remembered that the pickup assembly is tied to 4 major external circuits: laser power control, signal processing, focus, and tracking. All external circuitry should be eliminated as the cause of the problem before pickup assembly replacement is considered. In addition, there are several mechanical adjustments affecting the operation of the pickup assembly. Mitsubishi has used 2 basic types of pickup assemblies, an earlier version which incorporates a tracking mirror, and a later version that has no tracking mirror but a complete self-contained optical unit within the assembly. This is a simplified drawing of an earlier version pickup assembly. When enabled, the laser diode generates light which is directed to a diffraction grating or plate. The grating splits the laser beam into 3 separate beams. The center beam is utilized to convey digital data and focus error data. The digital data from the disk forms the HF signal, which is directed to the signal processing circuitry, and the focus error signal is applied to the focus circuitry. The 2 outer beams are used to form the tracking error signal, which of course is directed to the tracking circuitry. On the majority of CD players, the diffraction grating is adjustable and does have a great effect on tracking. All 3 beams from the diffraction grating pass through a polarized mirror to the tracking mirror. The tracking mirror deflects the beams through the lens to the disc. Reflected light from the disc passes back through the lens, is deflected by the tracking and polarized mirrors to the photodetector assembly. The photodetector converts the light signals to three electrical signals: digital data, focus error, and tracking error, that are output from the pickup. The three signals are too small to view directly out of the pickup, but may be viewed after amplification. The digital signal is denoted as the high frequency HF or radio frequency RF signal. The HF signal is the familiar I pattern used for many of the adjustments in the disc player. The focus error FE and tracking error TE signals appear to be random noise. Their amplitudes depend on the degree of error. Focusing is achieved by moving the lens in a plane perpendicular to the disc. The lens position is controlled by the focus control FC voltage from the focus circuitry, which is covered in Section 3. Tracking is achieved by varying the inclination of the tracking mirror, which in turn moves the laser beam horizontally across the disc. When the tracking mirror reaches the end of its range, momentary drive is applied to the slide motor, which moves the complete pickup assembly slightly. At the same time, the tracking mirror is reset to its starting position, and the cycle is repeated. The mirror inclination and slide motor are controlled by voltages developed in the tracking circuitry, covered in Section 4 of the tape. On later version pickup assemblies, there is no internal tracking mirror. There is a self-contained optical unit internal to the pickup. The optical unit contains the laser diode, diffraction grating, polarized mirror, lens, and photodetector. To maintain focus and tracking, the complete optical unit is moved. Focus correction voltage moves the unit in a plane perpendicular to the disc, and tracking correction voltage moves the assembly parallel to the disc. On the later version of pickup assemblies, the preamplifiers for the HF, focus error, and tracking error signals are internal to the pickup assembly. Therefore, all three signals may be viewed on an oscilloscope directly out of the pickup. The amount of laser power emitted from the pickup assembly lens varies between the various model CD players. The value for each model player is given in its respective service manual. If there is no laser output from the lens, the unit will register error and go into the stop mode. If the laser power is too low, focus and tracking may not be achieved, and the amplitude of the HF signal will be low. If laser power is excessive, both tracking and focus error signals will also be excessive, and usually tracking will not be maintained, causing error to be registered. Although the procedure for checking and adjusting laser power is similar on all CD players, refer to the service manual for the specific model. Laser power is measured without inserting a disc in the unit. On some models, the disc clamp assembly must be removed to give access to the pickup lens. To activate the laser, the disc sensor photodetector must be covered with tape. Power to the laser is usually activated by shorting two test points given in the service manual. Some units are designed with built-in test modes. Refer to the service manual for the test mode activation procedure. When the laser is enabled, insert the laser power meter sensor in front of the lens and read the power reading on the meter. If the power is incorrect, rotate the laser power adjustment until the reading corresponds to that given in the service manual. Laser power range usually falls in the area of 0.3 milliwatts to 0.4 milliwatts. One of the most important operations carried out by a CD player is altering the focal point of the pickup assembly to focus the laser beam. Until acceptable focus is achieved, and the microprocessor is notified of this fact, the play operation will generally be terminated. This section will explain the operation of the circuitry responsible for the focusing operation, beginning with the first step in the operational sequence of the CD player, reading the table of contents on the disc. If the disc player will not read the table of contents on a disc, It usually points to a problem in the focus circuitry, a servo system that controls the position of the pickup assembly in relation to the disc to assure that the laser beam generated by the pickup is sharply focused. A marginal focus problem may show up as track skipping or intermittently registering error during play. A thorough understanding of the operational sequence of a CD player is extremely valuable when troubleshooting the focus servo circuitry. Therefore, let's review in greater detail the operational sequence of most disc players. When a disc is inserted, the lens in the pickup assembly searches for good focus. On some players, focus search is not activated until the play button is pressed. If focus is not found, the unit registers error and stops. If rough focus is achieved, the focus servo is enabled and the laser beam is precisely focused. If sharp focus is not achieved, the unit registers error and stops. When sharp focus is achieved, the disc momentarily rotates and the table of contents is read. After the table of contents is read, the unit goes into the stop mode or directly into play, depending on the design of the player. Correlating the operational sequence to the basic block diagram of the focus circuitry, the drawer and disc sensors inform the control circuitry that a disc is inserted in the unit. The control circuitry responds by generating a focus search command. The search circuitry drives the lens through its range, attempting to find a rough focus point. As the lens searches, the autofocus OK circuitry, sometimes referred to as HFOK, monitors the audio data from the disc, denoted as the high frequency or HF signal. As the focal point is approached, the HF output voltage increases. When the autofocus OK circuitry senses the presence of the HF output, it generates a logic change on the AF-OK line, informing the control circuitry that rough focus has been attained. If the focal point is not detected, the lens is driven through the search cycle 3 times. Following 3 search cycles, if the rough focal point is still not detected, the unit will register error and stop. Also, if the lens does not move smoothly up and down during these focus search cycles, the lens might miss the optimum focus point and the player will again register error. Once the rough focus point is detected, the control circuitry terminates the search command and generates logic on the focus on line to enable the focus servo circuitry. The focus servo amplifies the focus error voltage from the pickup assembly and directs it to the lens drive in the pickup as the focus control or FC voltage. When sharp focus is achieved, the focus OK circuitry generates a logic change on the focus OK line, informing the control circuitry that sharp focus has been attained. On some players, the focus OK line is denoted as focus 0 cross. The control circuitry responds to the logic change on the focus OK line by generating momentary commands, enabling the tracking and disk drive servos. The disk momentarily rotates and the table of contents is read. On later disk players, fewer discrete components are used and most of the command and status data is transferred over serial lines. On these players, the control microprocessor is informed that a disk is inserted by the logic on the drawer sensor and disk sensor lines. The microprocessor responds by generating a focus search command. On this type of player, all commands between the microprocessor and the servo IC are transmitted on a single serial data line, usually denoted as data out or microprocessor serial data, MSD. The logic on the command data line is constantly changing and is present only during the reading of the table of contents or while accessing the play mode. A serial clock signal is utilized to time the transfer of data from the microprocessor to the servo IC. The clock signal is present only during the transmission of data. The microprocessor also generates a latch signal which enables the servo IC to accept commands from the microprocessor. The latch signal is usually denoted as MLA or XLT and is also present only during the time of data transmission. All three signals, data, clock, and latch, must be present in order for the servo to accept a command. Although only the focus circuitry is shown in the servo IC in this diagram, in most players the tracking servo is also internal to the IC. When focus search is activated, lens drive is generated from the focus correction output of the IC and is directed to the focusing coil in the pickup assembly. The HFOK circuitry is usually internal to the preamp IC, and its output is directed to the servo IC. The servo IC then informs the microprocessor that focus has been found by way of a serial servo status line, usually designated as a sense or servo data out. Only the momentary change on the status line can be checked in this system. When informed that focus has been found, the microprocessor generates commands to activate the focus servo. At the same time, commands are generated to activate the tracking and disk drive servo. The disk then rotates and the table of contents is read. The unit then goes into the stop mode or continues on into play, depending on the design of the player. Any malfunction during this operational sequence will cause the player to register error. By noting the point in the operational sequence where error is registered, the section of the focus circuitry causing the problem can usually be localized. If the table of contents is not read, note whether or not the disk rotates. If the disk does not rotate, check the search and HFOK circuitry. To do this, activate the focus search mode without inserting a disk in the unit. The disk sensor circuit must be activated. Various types of disk sensors have been used in different models. An optical sensor can be activated by covering the phototransistor with black tape. If a mechanical switch is used, merely short across the switch. On some units, the focus search cycle itself is used as the disk sensor, so it will automatically go into the focus search mode. When the disk sensor is activated, close the drawer and observe the lens. It should cycle through its range 3 times. If the lens does not cycle, check the search circuitry. On older players with more discrete components, check for the focus search command from the microprocessor. If the command is present, check the search drive circuitry and the pickup assembly. In checking the pickup, check for an open focus coil and make sure the lens assembly is not frozen in position. If no search command is generated from the microprocessor, check the logic from the disk and drawer sensors. If the sensor logic is incorrect, check the sensors and their associated circuitry. If the sensor logic is okay, check the microprocessor. If the lens does not search on newer players, check for the presence of the serial command data, the serial clock, and the latch. If any or all of the 3 signals are missing, check the drawer and disk sensor logic. If logic is incorrect, check the sensors, but if the logic is normal, check the microprocessor. If the data, clock, and latch signals are all present, check for search drive at the output from the focus servo. If drive is present, check the pickup for an open focus coil and a frozen lens assembly. If no search drive is present, check the servo IC. If the lens searches but the disc does not rotate, use a laser power meter and check the laser power output as described in section 2 of the tape. If there is no laser power or the power is incorrect, check the laser power supply and the pickup assembly itself as described in section 2 of the tape. If laser power is normal, check the HF-OK status line. If there is no logic change on the HF-OK line, check the preamp, HF-OK circuitry, and the pickup. If there is a logic change on the HF-OK line, check the status of the autofocus OK line. On older players, merely monitor the AF-OK line for a logic change. On newer players, monitor the serial status line and ensure that data, even though momentary, is present. If AF-OK logic is incorrect or is missing, check the AF-OK circuitry on older players or the servo IC on more recent players. If the AF-OK logic appears to be present, the problem may be in the control microprocessor. If the table of contents is not read, but the disc momentarily rotates, the focus servo is probably at fault. Monitor the focus error voltage while the table of contents is being read. If the amplitude drops to approximately 0.2 volts or less, the problem may be in the tracking servo, which is covered in section 4. If the focus error voltage does not drop to 0.2 volts or less, the problem is in the focus servo. Basically, the focus servo amplifies the focus error voltage from the pickup assembly and directs it back to the lens control coil in the pickup as the focus control or FC voltage. The amplifier is divided into two major sections: a voltage amplifier to amplify the low amplitude focus error voltage from the pickup, and a power amplifier section to drive the lens positioning device in the pickup. If there is no focus error voltage from the pickup, the problem may be in the pickup assembly. If focus error voltage is present at the output of the pickup, but no focus control voltage at the output of the servo, look for a problem in the servo amplifiers. There are usually two adjustments associated with the focus servo. An offset adjustment compensates for component variances. Its purpose is to set the output of the voltage amplifier to 0 when focus is correct. A rough adjustment of the focus offset may be made while viewing the focus error voltage and adjusting the offset adjustment for a symmetrical and minimum amplitude focus error signal. A fine adjustment is usually made while viewing the HF signal in the signal processing circuitry and adjusting the offset for the sharpest eye pattern. The focus gain adjustment sets the level of the focus correction voltage feedback to the pickup. Of course, if the gain adjustment is too low, focus may be lost completely or intermittently, causing the player to register error or skip tracks, depending on the degree of the misadjustment. If the focus gain is set too high, a mechanical noise is generated from the pickup due to the extreme movement of the lens. A rough adjustment of the focus gain may be performed by increasing the gain until noise is generated from the pickup, and then backing off until the noise just disappears. If a problem still exists, such as intermittent error or track skipping, a precise focus gain adjustment procedure is given in the service manual. Since the procedure is not the same on all players, refer to the service manual for that particular player. Unlike a vinyl record, The compact disc does not have a groove for the pickup element of the player to follow. Therefore, the CD player requires an electronic tracking system to maintain alignment between the pickup assembly and the audio information on the disc. A tracking servo problem may show up as a multitude of symptoms: an inability to play any track of the disc, intermittent dropout or muting of the audio, an inability to perform the skip or search functions, or the player registering error while in play. A thorough understanding of the operating sequence of a CD player is extremely valuable for troubleshooting the tracking servo. Let's review this sequence and then look at the basic block diagram of the tracking circuitry. When the player loads a disc, the control system will first reset the servo systems to the start position. Focus, tracking, and disc servos will all be off, and the slide containing the pickup assembly will be set to the inside stop, which places the pickup at the lead-in track of the disc. This is the track closest to the disc center. Once the servo reset is complete, the laser is enabled and the lens in the pickup assembly searches for rough focus. Once the pickup lens is able to achieve rough focus, a logic change occurs on the AF-OK line, informing the control circuitry that rough focus has been attained. The control circuitry responds to the logic change by first generating a command to turn on the disc motor servo. Once the disc begins to rotate, the focus servo system is enabled. When best focus is attained, the focus OK line will change state and the control system responds by enabling the tracking servo. It is important to note at this point that portions of both the focus servo and the disc motor, or CLV servo, are included in the block diagram, since both of these systems must operate correctly before the tracking servo can be enabled. More recent disc players use fewer discrete components, and most command and status data is transferred over serial lines. More information on this process can be found in Section 3 of the tape. After being enabled, the tracking servo attempts to track and read the table of contents portion of the lead-in track. If the tracking servo is unable to track the pits that contain the data, the player will register error and stop. If proper tracking is achieved, the table of contents data is read, and the player will go into the stop mode or directly into play, depending on the design of the player. The tracking sensor portion of the pickup generates a tracking error signal denoted as TE on some models and TER on others. The output of the two tracking sensor diodes, E and F, will be equal whenever the laser beam is directly centered over the track. The tracking error voltage will be 0 under these conditions. However, if the tracking is offset from the correct path, the output of one sensor will be greater than the other, generating either a positive or negative tracking error signal, depending on the direction of the error. The error signal is amplified and directed to the tracking coil of the pickup assembly. The coil moves either the tracking mirror or the optical unit to achieve correct tracking. Note, however, that one additional signal is fed to the tracking servo, the HF signal from the disc. The tracking servo must monitor this signal since equal tracking sensor output, which denotes 0 tracking error, can occur at two places: when the pickup is directly over the track and when the pickup is directly between two tracks. If the pickup attempts to track between two tracks, the HF signal will not be present. The tracking servo will then generate kick pulses to nudge the pickup towards the track. Once the HF signal appears, the kick pulses are discontinued and the tracking servo operates normally. The tracking mechanism within the pickup assembly has only a limited range of movement, about 5 millimeters. This range is sufficient to accommodate the lead-in track, but insufficient to track the entire compact disc. An additional servo system called the feed motor, slide motor, or sled motor servo, depending on the player, performs this course tracking function. By moving the slide mechanism, to which the pickup is attached, the pickup assembly is kept roughly centered over the proper track as the disc is played. This servo is also responsible for the movements necessary for the reset, skip, search, and programmed play functions. As the tracking coil moves the tracking mirror or optical unit further from the center of its range, the DC average value of the tracking coil drive voltage increases. When this voltage rises to a point near the end of the tracking coil's range, the slide motor servo turns the slide motor drive circuit on. The slide will move, recentering the pickup over the track. In certain players, the slide motor servo is part of the tracking servo, and in others, part of the control system. Once the DC level of the tracking coil drive exceeds the threshold where coil drive is necessary, the coil drive will be removed while the slide motor drive is enabled. After the slide has been moved, tracking coil drive is resumed at a slightly higher than normal gain so that proper tracking can be achieved quickly. The data from the disc is then read and, if necessary, kick pulses are generated to place the pickup over the correct track. Normal tracking gain is then resumed. While the operation of the tracking servo is very similar in the skip and search modes, the actual on time of the slide motor drive will be determined by the control system of the player depending on the mode selected. By noting the point in the operational sequence where error is registered, the section of the CD player circuitry causing the problem can usually be localized. Certain players will not enable the laser if the slide does not reach the inside stop. Confirm that the slide is at its reset position. If the slide will not move to this reset position, check for mechanical problems such as binding, and then, if necessary, check the slide motor drive circuitry. If the table of contents is not read, note whether or not the disc rotates. If the disc does not rotate, check the focus and disc motor circuitry. Troubleshooting procedures for these circuits are described in sections 3 and 5, respectively. If the table of contents is not read, but the disc momentarily rotates, check the logic change on the control line that enables the tracking servo. If the logic on the control line does not change, check the focus servo. However, if the logic does change, the difficulty probably resides in the tracking servo. Basically, the tracking servo amplifies the tracking error voltage from the pickup assembly and directs it back to the tracking coil in the pickup. The amplifier is divided into two major sections: a voltage amplifier to boost the low amplitude tracking error voltage from the pickup, and a power amplifier section to drive the tracking coil in the pickup. If there is no tracking error voltage from the pickup, the problem may be in the pickup assembly. If tracking error voltage is present at the output of the pickup, but there is no tracking control voltage at the output of the servo, look for a problem in the servo amplifiers. There are three adjustments usually associated with the tracking servo. Remember that they may not be present on all players. The EF balance adjustment compensates for differences in the output of the two tracking sensor photodiodes, E and F. This adjustment may be made while viewing the tracking error voltage and adjusting the EF balance control for a symmetrical tracking error signal. The tracking offset adjustment compensates for component variances. Its purpose is to set the DC output of the voltage amplifier to 0 when tracking is correct. This adjustment is usually made with the player in the stop mode. The tracking offset control is then adjusted for a specific DC voltage, usually 0 volts, at either the tracking error signal test point or the output of the tracking coil drive amplifier. The tracking gain adjustment sets the level of the tracking correction voltage fed back to the pickup. Of course, if the gain adjustment is too low, the player will become extremely sensitive to vibration, and tracking may be completely or intermittently lost. If the tracking gain is set too high, a chirping noise will be generated by the pickup. This noise is due to the extreme movement of the tracking mirror in earlier model pickups and the optical unit in later versions. A rough adjustment of the tracking gain may be performed by turning up the control until noise is generated from the pickup. At this point, note the position of the control. Next, rotate the control in the other direction until the player starts to lose tracking. Note the position of the control again. Then place the control midway between the two positions. If a problem still exists, such as intermittent error or track skipping, a more precise tracking gain adjustment procedure is given in the service manual. Since the procedure is not the same on all units, refer to the specific service manual for that player. If the tracking error voltage from the pickup is excessive, even after these three adjustments, the diffraction grating inside the pickup may require adjustment. This is described in Section 6 of the tape. If the player will read the table of contents, but is unable to access the music tracks of the disc, or the skip and search features of the player fail to respond, a failure in the slide motor system is probably the cause. However, before assuming that the slide motor servo system is at fault, check to be sure that the mechanism transport locks are released. The slide servo amplifies the DC component of the tracking servo output, combines this with forward and reverse commands from the control system, then drives the slide to keep the pickup centered over the desired track of the disc. Once again, the amplifier is divided into two major sections: a voltage amplifier to amplify the low amplitude DC signal from the tracking servo, and a power section to drive the slide motor. If there is no signal from the low-pass filter reaching the voltage amplifier, the problem is either in the tracking servo section or the control system is not turning the slide servo on. If the error voltage is present at the input to the amplifier, but no slide voltage appears at the output of the servo, look for a problem in the servo amplifiers. If the player will track a disc, but the skip or search functions fail to operate properly, one or more of the control system outputs to the slide servo are probably incorrect. Check for the proper logic on these control lines. While the servo gain is fixed in the majority of CD players, some units have a control to adjust the slide servo offset. The SS offset adjustment compensates for component variances. Its purpose is to set the output of the voltage amplifier to 0 when the slide servo has no input. This adjustment is made with the player in the stop mode. The slide servo offset control is then adjusted for 0 volts DC at the output of the slide motor drive amplifier. On players with linear slide motors, the procedure is somewhat different, so consult the appropriate service manual on the complete procedure for the specific player concerned. The disk drive servo, also referred to as constant linear velocity, seldom gives problems. However, many symptoms encountered while servicing disc players include no disk rotation. In the majority of cases, no disk rotation is not usually due to a defect in the disk drive servo, but results from the circuitry not being enabled. Remember, focus must be found before the disk servo is enabled. Therefore, if the disk does not rotate, first determine if focus is attained. If focus is not found, troubleshoot the focus servo as described in Section 3 of the tape. If focus is achieved, check whether or not the disk servo is enabled. The disk servo enable may be one or more command lines from the control circuitry, or, on later model players, may be a single serial data line. If the disk servo is not enabled, check the control circuitry of the player. If the servo is enabled, check for an output from the servo circuitry. If a servo output exists, the problem is in the disk motor drive or the motor itself. If no output is detected from the servo, check the disk drive servo circuitry. The disk drive servo is comprised of 4 basic sections: a start-stop circuit, an automatic frequency control or AFC circuit, a constant linear velocity or CLV circuit, and the disk motor drive circuit. The start-stop circuitry generates the initial drive to start the motor rotating. The automatic frequency control circuit roughly brings the motor to correct speed, and the constant linear velocity servo controls the disk's rotational speed so a constant linear velocity is maintained. The CLV servo is basically a phase lock loop configuration. As in all PLL circuitry, a comparison signal of the controlled device is compared against a standard reference, and if a difference exists, a correction voltage is generated. In the CLV servo, the comparison signal must indicate the disk's current linear speed, that is, the rate at which the disk passes under the pickup. The comparison signal is derived from the PLL clock oscillator in the signal processing circuitry. The PLL clock is synchronized to transitions in the data train from the disk, and when the linear velocity is correct, the clock frequency is 4.321 MHz. The stable reference is derived from a crystal-controlled 8.46 MHz oscillator, usually internal to the signal processing demodulator IC. Divided samples of the comparison and reference signals are compared in the CLV servo, and if a difference in frequency or phase exists, a correction voltage is added to the disk drive. The disk motor drive circuitry is a power amplifier, amplifying the CLV correction voltage and directing it to the disk motor. The output of the CLV circuit is an analog voltage on earlier model units and a pulse width modulated signal on later version players. Let's follow the basic block diagram of the disk drive servo during the normal operational sequence. When focus is attained, the control circuitry enables the start-stop circuitry to initially start the motor's rotation. Immediately afterwards, the AFC circuitry is enabled. The AFC circuitry utilizes the sync signals at the start of each audio frame on the disk. The frame synchronizing signals are separated from the rest of the HF signal and are directed to the AFC circuitry. The AFC circuitry determines the initial rough drive for the disk motor from the frequency of the frame sync signals. When disk speed is correct, the frame sync frequency will be 7.35 kHz. On most players, the frame sync signal also serves as the disk rotation detector. If the sync is missing, drive to the disk motor will automatically be removed. After the rough disk speed is attained, the CLV servo is enabled to maintain a constant linear velocity by altering the disk motor drive. On early model units, using more discrete components, each enable signal may be checked individually. Later versions incorporate a single serial command line, which is discussed later in this section. On many players, the frame sync is utilized as the comparison signal in the CLV circuit, representing the disk speed, rather than an actual division of the PLL oscillator. On earlier model players, the reference and comparison signal were usually designated as read frame clock, or RFCK, and write frame clock, or WRFCK, respectively. Both signals are output from the signal processing demodulator IC and directed to the CLV circuit. Also, on earlier units, AFC and CLV, or APC adjustments, were included. Due to the variations in design, refer to the service manual for each specific player for the correct adjustment procedure. Usually, the only adjustment in the disc servo is the free-running frequency of the PLL oscillator, and on many later model units, this adjustment has been eliminated. The PLL oscillator adjustment is performed by removing the HF signal from the input of the PLL oscillator and setting its frequency as close as possible to 4.321 MHz. Refer to the service manual for each specific model. But in general, the procedure usually involves shorting a test point to ground and adjusting the frequency of the oscillator to 4.321 MHz on a frequency counter. To electrically check if the disk drive is correct, check for synchronization between the PLL oscillator and the HF signal. Connect one channel of an oscilloscope to the output of the PLL oscillator. Connect the second scope input to the HF signal test point. Trigger the scope from the PLL oscillator output and set the repetition rate to the digital frame rate 7.35 kHz. When the two signals are in synchronization, the HF signal will remain stationary and not drift across the screen. On later model units, the disk drive servo is internal to the signal processing demodulator IC. The servo is controlled by a serial data line from the control circuitry, usually denoted as data or MSD, microprocessor serial data. The timing for serial data transfer is controlled from a serial clock signal, also generated by the control circuitry. The signal processing IC is enabled to accept disk servo commands by a latch line usually denoted as MLA or XLT. These are the same control lines that control the focus and tracking servos in the servo IC. Since all data is serial, all that can be checked is that a change in data occurs, as described in Section 3. If the unit searches for focus, the three lines, data, clock, and latch, are probably okay. However, if the microprocessor is not informed that focus is okay, it will not generate disk servo or tracking servo enable signals. Therefore, ensure that a data change occurs on the status line between the servo IC and the control microprocessor. On many later models, the PLL oscillator is internal to the signal processing IC and cannot be viewed with an oscilloscope. On these units, the logic on a status output from the signal processing IC, usually denoted as GFS or SYCLK, denotes whether or not the disk is rotating at the correct speed. When correct, the status line logic goes high. The sync lock logic is directed back to the control microprocessor. If the line does not go high, the control circuitry automatically activates the stop mode. The output of the CLV servo is amplified by the disk motor drive and is directed to the motor. On early model units, the CLV output is an analog voltage. Later version players utilize digital servos, and the output of the CLV is usually a pulse width modulated signal. In many cases, two PWM signals are generated 180 degrees apart. If the CLV circuitry is responding, the duty cycle of the PWM signal should change when the disk is manually slowed. This is a good check to determine if the CLV circuit responds to changes in disk speed. If the CLV responds to disk speed, the problem may be in the disk motor drive, where conventional troubleshooting techniques may be used. The mechanical adjustments in a disk player can be divided into two major groups, those affecting the pickup assembly operation and those dealing with loading and unloading a disk from the player. Three mechanical adjustments affect the operation of the pickup assembly: the disk height, jitter, and the internal diffraction grating. The design of the individual player will determine which of these adjustments are required. All three adjustments may not be possible on all players. The disc or turntable height adjustment determines the distance from the pickup assembly lens to the disc. If the distance is incorrect, the player will not be capable of finding good focus during the focus search cycle, and the player will register error. Usually, the adjustment requires loosening a set screw in the turntable and adjusting the height to the value specified in the service manual for that specific player. Any mechanical problem that affects the turntable height can also prevent focus from being achieved. This is an especially important point to remember if the player has no turntable height adjustment. Most players do have a jitter adjustment. This adjustment sets the plane of the pickup assembly parallel to the disc. The jitter adjustment is made while playing a disc and viewing the HF signal eye pattern on an oscilloscope. Rotate the jitter adjustment for optimum eye pattern, adjusting for minimum jitter and equal amplitude. Although all pickup assemblies have a diffraction grating, the adjustment itself is not always accessible. While an incorrect grating adjustment affects all signals from the pickup, it usually affects the tracking error signal to a greater degree. Therefore, a diffraction grating problem usually appears to be a tracking problem. In general, the grating adjustment is performed while viewing the tracking error voltage and adjusting the grating for minimum amplitude tracking error. Of course, when making the adjustment, refer to the appropriate service manual for the specific adjustment procedure. Some units incorporate special test modes for making adjustments. When in a test mode, the diffraction grating is usually adjusted for maximum amplitude tracking error signal. Before most adjustments can be performed, a disc must be inserted in the player. Typically, this involves opening the drawer, inserting a disc, and then closing the drawer. The drawer operation is generally monitored by two status sensors, a drawer open sensor and a drawer close sensor. The open and close sensors are usually mechanical switches activated by the position of the drawer. On many disc players, the positioning of these switches is adjustable, so refer to the player service manual for the correct adjustment procedure. If the close switch is defective or misadjusted, the drawer will usually close, but will automatically open again within a few seconds. If the open switch is defective or misadjusted, the opposite symptom usually occurs. The drawer will open, then automatically close. On some units, an open switch problem will allow the drawer to open but not to be closed, since the switch position leads the control circuitry to believe that the drawer is already closed. A third mechanical sensor is used in the player to sense when the pickup assembly is at the start or center of a disc. The sensor is usually a mechanical switch known as the inner switch and may or may not be adjustable depending on the player. Two symptoms are generally associated with a defective or misadjusted inner switch. If the inner position of the pickup is not detected, the pickup slide drive is not removed and the mechanism usually jams or freezes. If the inner switch position is incorrect, the pickup assembly will not be positioned over the start of a disc, the table of contents will not be read, and the player will register error. Usually, the pickup is reset to the inner switch position when power is turned on or when stop is activated when playing a disc. On some units, the drawer will not open or close if the inner switch position is not detected. On earlier players, the open, close, and inner switches controlled the logic at an input of the control microprocessor, generating either a high or low. On later players, the three sensor switches either direct or remove a scanner signal from the microprocessor scanner input port. Since all three of the sensors are mechanical and monitor the mechanical operation of the unit, they are a principal source of problems in a disc player.